So let's go over this review problem, and this is mostly a review of the definition of roots and also raising powers to fractional exponents, which are slightly different in some cases. First off, the easy ones. The cube root of 64 is clearly equal to 4, and 64 to the 1/3 power is equal to 4. 60 square root of 64 is equal to 8. And 64 to the 1/2 is also equal to 8. So for the case of positive number, there's no distinction between these definitions. Where it gets interesting is if numbers are permitted to be negative. The cube root of negative 64 is equal to negative 4. If I take negative 4 to the 1/3 power, so negative 4 to the third, that is equal to negative 64. And so the cube root of negative 64 is negative 4, as you would expect. However, negative 64 to the 1/3 power is going to be something different. When we use this notation, negative 64 to the 1/3, we're going to be using de Moivre's theorem. So let's explain how this is going to go. Negative 64 is equal to 64 times negative 1, which is 64 times e to the I pi. And so I'm trying to solve z cubed. Now let me get some extra space here. I'm trying to solve z cubed equals 64 times e to the I pi. And so if we let z be equal to r times e to the I theta, this reduces to solving r cubed times 3I theta equals 64 e to the I pi. So that means that r cubed is 64, and 3 theta is equal to pi plus 2 pi n. R must be positive, and so that means r is equal to 4, and the angle theta is equal to pi plus 2 pi n over 3. Okay, so that's the property, so let's actually do the computations. So if n equals 0, that means that z is equal to 4 times the cosine of pi over 3 plus I sine pi over 3, which is 4 times a half plus I square root of 3 over 2, which is 2 plus 2I square root of 3. Next, if n equals 1, then we have z is equal to 4 times the cosine of pi plus I sine pi, because if n equals 1, then we'd have 3 pi over 3, which is pi. That works out to be 4 times negative 1 plus 0I, which is negative 4. And we've seen that before, negative 4. N equals 2. If n equals 2, we have 5 pi over 3 as the angle, so z is equal to 4 times the cosine of 5 pi over 3 plus I sine 5 pi over 3 and that works out to be 4 times a half minus I square root of 3 over 2, which is 2 minus 2I square root of 3. Okay, now I didn't have to do all this work to answer the question, but I wanted to do the work to show where it comes from. Negative 64 to the 1/3, when I take a number to a fractional exponent, that means, by definition, I take the n equals 0 one when I do de Moivre's theorem. So the answer to this one is equal to 2 plus 2I square root of 3. And I choose this one because the angle pi over 3 is the smallest. So the important distinction is that when I write this root notation, that means I need to take a real number as an answer if possible. When I write the fractional notation, that means I want the number with the least angle. And pi over 3 as an angle is less than pi. For positive numbers, positive real numbers, the two definitions are absolutely identical. But for negative numbers, they're different. Now, to go over why they're identical, let me take, say, 64, positive 64. So I'm going to go back and look at 64 to the 1/3. So suppose I'm solving z cubed equals 64, and I do the plus 64 case in very much the same way that I did the negative 64 case. Then this is that r to the third times e to the 3i theta is equal to 64 times e to the 0i. Because the angle in question is, because 64 is 64 times 1 plus 0i. So that means I need r cubed is equal to 64. And also I need 3 theta to be equal to 0 plus 2 pi n. So r is equal to 4. And theta is equal to 0 plus 2 pi n over 3. So the smallest angle occurs when n is equal to 0. I'm not going to do the other two. N equals 0. That means that z is equal to 4 times cosine of 0 plus I sine of 0, which works out to be 4. And so because that's 4, that's the number that goes right there, 4. So in the positive case, the two definitions are equivalent. In the negative case, they are not. And that's because in the positive case, the angle in question is 0. But for the negative case, the angle in question is pi. And so it's I get a complex number as my answer. Just to go over, to show that this actually works on the calculator. This is not a proof, but it shows why the calculator works the way it does. Let's take negative 64 raised to the 1/3 power, the way that we ordinarily do it. Then this is negative 4. Written this way, that is interpreted to be the cube root of 64, the way that we ordinarily think of a cube root. However, if I go negative 64 plus 0i raised to the 1/3, this forces the calculator to think about the second interpretation of raising a number to the 1/3 power, and I get the different answer, 2 plus 2 square root of 3 times I. So that's an explanation as to why these two apparently equivalent expressions are returning different answers on the calculator. Okay, so let's now take a look at the remaining problems. The square root of 64 is not defined. there is no real number that when you square it, you get negative 64. However, we can define negative 64 to the 1/2 power. And the way that we do that is negative 64, as we saw before, is equal to 64 times e to the I pi. So if I want z squared to be equal to this, then that means r squared times e to the 2I theta has to be equal to 64 times e to the I pi. So r squared is equal to 64. And we also have that 2 theta is equal to pi plus 2 pi n. So r is equal to 8. And theta is equal to pi over 2, or pi plus 2 pi n over 2. So the n equals 0 case provides the answer to what it is when I raise to the 1/2. So z is equal to 8 times cosine pi over 2 plus I sine pi over 2 which works out to be 8i. And so negative 64 to the 1/2 is defined to be 8i, even though the square root of 64 is undefined. Now let's see if that happens on the calculator also. So negative 64 to the 1/2, ordinary definition of square root, is undefined. But if I take negative 64 plus 0i to the 1/2, that returns 8i. So we get different answers to these two apparently equivalent expressions because two different definitions are being used for the operation. The first one is square root of negative 64. The second one is negative 64 raised to the 1/2 power. And those are slightly different answers based on the fact that the different ways that they're computed. Finally, let's take a look at this last expression, where I have a complex number. The first one, negatives to minus 2I squared root of 3 square root, this is not defined. We only consider this root operation to work for real numbers, not complex numbers. The second one is obtained in very much the same way that we did the last couple. So negative 2 minus 2I squared root of 3 is down here in the complex plane. So the distances in question are negative 2 and negative 2I squared root of 3. So the distance from the origin is 4, and the angle is 4 pi over 3. So we're solving z squared is equal to 4 times e to the 4 pi I over 3. And so that means I want r squared times e to the 2I theta to be equal to 4 e to the 4 pi I over 3. So r squared is equal to 4. And 2 theta is equal to 4 pi over 3 plus 2 pi n. So I have r equals 2. And we also have that theta is equal to 2 pi over 3 plus pi n. And I would let n equal 0 and n equal 1 if I wanted both roots If I want the one root that's defined to be the number raised to the 1/2 power, I take n equals 0. So that gives me z is equal to 2 times the cosine of 2 pi over 3 plus I sine 2 pi over 3 which is 2 times negative 1/2 plus I square root of 3 over 2, which is negative 1 plus I square root of 3. And let's check that actually works, or matches what the calculator says. If we take negative 2 plus 2 times I times the square root of 3 and raise it to the 1/2 power, then we do indeed get 1 plus square root of 3 times I. So that's the how to do these particular problems. And so let me mark that as the answer, negative 1 plus I square root of 3.